Welcome. Okay, this is a bit of a special Mathologer today. A number of you have requested that I do something on blackjack and card counting. So here we go. How to gamble yourself to fame and fortune. I am being assisted today by fellow mathematician, longtime colleague and part-time gambler Marty Ross here, who is really good at this stuff and who has offered to share some of the mathematical secrets to coming out on top in gambling games like blackjack. Okay, so let's begin with a couple of puzzles. For the first puzzle, suppose you're looking to bet on roulette. The roulette wheel is numbered from 0 to 37 with 18 red numbers, 18 black numbers and the green 0. So the chances of red coming up is just under 50-50. Now let's suppose you've been watching the roulette wheel and of the last 100 spins, red has come up 60 times. What should you bet will come up next? Red? Black? Doesn't matter? Sounds too easy? Well, this probably comes as a surprise, but most people get this one wrong. We'll give the answer in a little while. Our second puzzle actually arises in practice, a standard way that casinos and gambling sites sucker people into betting. For this puzzle, you're given a $10 free bet coupon. You can use the coupon to place a bet on any standard casino game, roulette, blackjack, craps and so on. If your bet wins, then you receive the normal winnings. For example, let's say you bet red on roulette. If red comes up, you win, $10 of course. Win or lose, the casino takes the coupon. Now here's the question, what is the value of this coupon? In other words, what should or would you be willing to pay for such a coupon? We leave that one for you to fight over in the comments, but we'll give you a hint. Whatever you think the obvious answer is, you're definitely wrong. Now, on with making our fortune. Famously, the mathematician Blaise Pascal sorted out the basics of probability in order to answer some tricky gambling questions. We're not dropping rocks. Galileo also dabbled in these ideas, so if we roll a standard die, then there's a 1 in 6 chance that 5 will come up, and on a roulette wheel, there is a 1 in 37 chance that 13 comes up. Usual stuff. Then comes in the money. What really matters to a gambler is not only the odds of winning, but of course also how much they get paid if they win, right? And that's the idea of expectation, the expected fraction of the gambler's bet he expects to win or lose. As an easy example, suppose we bet $1 on red on roulette. We have an 18 in 37 chance of red, in which case we win $1. There's also a 19 in 37 chance of losing $1. And so if we keep betting $1 on red, on average, we expect a loss of 18/37 minus 19/37, which is minus 1/37 of $1, or minus $0.03. What this tells us is that in the long run, we expect to have lost about 3% of whatever we've bet. 37 spins, and we expect to have lost about $1. 370 spins and we've lost about $10 and so on. Of course, dumb luck can mean that the actual amount we might win or lose may vary dramatically. Again, in maths, we express all this by saying that the expectation of betting on red is minus 1/37 or minus 3%. As another example, what if we bet that the number 13 comes up? If 13 comes up, we win $35. And there's a 1 in 37 chance of that. There's also a 36 in 37 chance of losing our dollar. And so our expectation comes to 35 or 37 minus 36 or 7, which, as in the first roulette game that we considered, is equal to minus 1/37. In fact, no matter what you bet in on roulette, the expectation will always be minus 1/37, give or take some concedo variation. Expectations can vary dramatically on gambling games, from close to 0% on some casino games down to minus 40% or so on some lotteries. But, unsurprisingly, the expectation is pretty much guaranteed to be less than 0, and minus means losing. So far, so really, really bad. What can we do about it? Well, a popular trick is to vary the size of your bet, depending on whether you win or lose. The most famous of such schemes is the so-called Martingale. This betting scheme works like this. As before, let's bet on red in roulette, and let's start by betting $1. If red comes up, you win $1 and you repeat your $1 bet. If red does not come up, you lose your $1. To make up for your loss, you play again, but this time with a doubled wager of $2. If red comes up, you win $2, which, together with the $1 lost in the previous game, amounts to an overall win of 2 minus 1 is equal to $1. So you've won, so you go back to betting just $1. On the other hand, if red does not come up, you lose your $2, which then adds up to a total loss of 2 plus 1 is $3. You've only lost so far, so you play again, but this time with a double wager of $4. If red comes up, you win $4, which together with the $3 loss so far means that overall you've won $1. You've won, and so you revert to betting just $1. On the other hand, if red does not come up, you lose your $4, which then adds up to a total loss of 4 plus 3 equals $7. So far you've only lost, so you play again, but this time with a double wager of $8, etc. So basically you keep doubling your bet until your bad luck runs out, at which time you start from the beginning by betting $1 next. Then keep doubling your bet again until you win, and so on. As long as you stop playing after some win, this betting strategy seems to guarantee you always coming out on top overall. There are many such betting schemes, the d'Alembert, the reverse Labouchet. Apparently these schemes work much better if they have fancy French names, believe it or not. But do bet variation schemes work? Probability questions like this one can be tricky, depending in a subtle way on our assumptions. The Martingale, for example, obviously works if you happen to have infinity dollars in your pocket. But then why bother gambling? And of course, whatever you do, you can always get lucky. But with a finite amount of money in your pocket, what can we expect to happen? Well, suppose we make a sequence of bets with the same expectation E for each bet, as in the setup we just looked at. Then the total amount we expect to win or lose is easily calculated. It's just E times that positive number there, and if E is negative, then no luck. That brings us to the fundamental and very depressing theorem of gambling. The theorem says that if the expectation is negative for every individual bet, then no bet variation can make the expectation positive overall. Damn! Okay, so we're not going to get rich unless we somehow find a game with positive expectation. For the moment, let's just assume that such a game exists. How well then can we do? Suppose we're betting on a casino game for which the chances of winning are 2/3, and therefore the chance of losing are 1/3. Let's also assume that just like in betting on red in roulette, you win or lose whatever amount you bet. Then the expectation for this game is actually positive. To be precise, it's a whopping 33%. Now, such a huge positive expectation in the casino game is clearly a fantasy, but bear with us, okay? Suppose we start with $100. What are the chances of doubling our money to $200? Well, obviously, if we just plonk it all down in one big bet of $100, then the chances of doubling are, well, 2/3, of course. This may come as a surprise, but we can actually improve our chances if we bet $50 at a time and we play until we either bankrupt or we have doubled our money. Let's do the maths. If we place $50 after one bet, win or lose, we either have $150 or $50. And after two bets, we have $0, $100 or $200. Now, reading off the tree, we see that at this point, the probability of having doubled our money in the first two plays is 2/3 times 2/3, which is equal to 4/9. And similarly, the probability to be back to where we started from with $100 is, well, 2/3 times 1/3 plus 1/3 times 2/3, which happens to also be 4/9. But if we're back at $100, we can keep on playing until eventually we have doubled our money or are bankrupt. This can actually take a while before this is sorted out, right? Now, if D are the chances of eventually doubling our money, in this way, then D is equal to what? Well, 4 nines, the probability of having doubled our money after 2 bets, plus the second 4 nines, the probability of being back where we started from, times the probability to be able to double from this point on. And what is that? Well, we're back to $100, so the probability is D again. That's actually quite a nifty calculation when you think about it. Anyway, now we just have to solve for D, and this gives that D is equal to 4/5, which is 80%. And this is definitely a lot better than the 66% that going for just one bet of $100 guaranteed. Repeating the trick, we can consider betting $25 at a time. This results in an about 94% chance of doubling our money. In fact, by making the bet size smaller and smaller, we can push the probability of us eventually doubling our money to as close to certainty as we wish. And once we've doubled our money, why not keep on playing to quadruple, octuple, etc. our money? And since we can push the probability of doubling our money to close to uncertainty as we like, the same is then also true for any of those more ambitious goals. Even better, the same turns out to be true no matter what probabilities we're dealing with, as long as the expectation of the game we play is positive, as in the game that we just played. The very surprising conclusion to all this is our second, very encouraging theorem of gambling. So here we go. If the expectation is positive, then we can win as much as we like, with as little risk as we like, by betting small enough for long enough. And so finally, a bit of very good news, right? All right, so all that's holding us back from fame and fortune is finding a game of positive expectation. For that, of course, we again turn to the game of roulette. No, just kidding. And we'll get back to blackjack in a minute. But there are many approaches to gambling, and one factor to keep in mind is that games like roulette are mechanical, which means the true odds aren't exactly what the simple mathematics predicts. Is this sufficient to get an edge on the game? Well, I won't go into that today, but in the references you can find some fascinating stories of people who've tried to, and occasionally succeeded, in beating the casino in this way. And such attempts continue to this day. And with that in mind, we'll now answer our roulette puzzle from the start. So, if 60 of the last 100 spins have turned up red, then you should most definitely bet on, well, red of course. Feel free to disagree vehemently in the comments. Okay, so finally on to making our fortune at blackjack, a possibility made famous in the Kevin Spacey movie 21. Well, Kevin's out of favor now, so you should watch The Last Casino instead. It's a much better movie anyway. For this video, you don't really have to worry too much about the rules of blackjack, so here's just a rough sketch. Now, blackjack is played with a standard deck of 52 cards, or nowadays a number of such decks. The goal is to get as close to 21 without going over. Here, all face cards count as 10. The aces count as 1 or 11. The player can actually choose whichever works better for them. In blackjack, you're playing against the dealer. You're initially dealt 2 cards, and the dealer just 1. All face up for everybody to see. You go first. You can ask for more cards one at a time until you either bust, which means you go over 21, in which case you lose immediately, or you stop before this happens. Then it's the dealer's turn, who will deal herself cards like a robot until she hits 17 or above and then stops. The person closest to 21 without having gone bust wins. The casino's edge comes from you, the player, having to go first, knowing only the dealer's first card. So if you bust by going over 21, then you lose immediately, even if the dealer later busts as well. There are, however, some compensating factors that favor the player, including the ability to make decisions such as when to stop receiving cards and whether to split or to double. Well, we won't go into this. Actually, the ability to make decisions only favors the player if they know what they're doing, which is actually hardly ever the case. The fundamentals of optimizing blackjack play involve knowing what decisions to make given any total of your cards and whatever the dealer's card. And this is known as basic strategy, and was actually first figured out in the 1950s by some army guys playing with their new electronic calculators. The basic strategy can be summarized in a table which all expert players know by heart. Here's a simplified version. Let's use it. At the moment, our cards add up to, well, 10 for the queen, plus 5, that's 15. So look up 15 on the left side. The dealer has 8. And so the basic strategy tells us that we should hit, which means ask for another card. Let's do that. Now we've got 19, and this means that the basic strategy tells us to stand or stop, which of course makes total sense at this point in time. Figuring out the basic strategy just involves a lot of easy probability, tree diagrams and such stuff. Casino rules can differ, which then changes the basic strategy slightly, as well as the resulting expectation. But in a not too nasty casino, the expectation, given optimal play this way, might be about minus 0.5%. Close, but no banana. Of course, plenty of people do worse than that. Casinos play their cards close to their chests, but it seems that on average the casinos make well over 5% on blackjack, a clearly better rate of return for the casino than on roulette. Anyway, if we want to make our fortune, we have to somehow get around that minus 0.5%, and that's where card counting comes in. Card counting arose in the early 60s, courtesy of mathematician Edward Thorpe. And the fundamental idea is very easy. Basic strategy assumes that any card has an equal likelihood of appearing next. Well, that's a fairly natural assumption to make if there is no other information to be had. But of course there is other information to be had. As cards get dealt, the probabilities change. In general, high cards are better for the player and low cards are worse. Then, as the cards are dealt out, the expectation changes, and the expectation will be positive if sufficiently many low cards are dealt. That sounds like a lot of information to keep track of, but counting simplifies it all down to keeping track of just one number called the running count. Every time the cards are shuffled, the running count resets to 0. After the shuffle, whenever you see a low card, you add 1 to the running count. Whenever you see a high card, you subtract 1. Otherwise, you don't do anything. The running count indicates how many extra high cards there are among the cards left to be dealt. Keeping track of the running count may seem tricky to do in a casino with all the cards zipping around on the table, but it's actually pretty easy. Watching a blackjack table for about an hour, most people can keep track of the running count pretty accurately. There are also plenty of apps around, like that one there, if you want to practice in the safety of your home, or you can just get a plain old deck of cards. Now, were any of you fast enough to keep track of the running count just now, over there? Well, I showed this one to Marty cold and he just had it straight away. Anyway, what we really want to know is not the number of extra high cards left to be dealt, but the fraction of extra high cards remaining. For example, 5 extra high cards matter much less if they're within 3 decks left to be played than if there's only 1 deck left to be played. To account for this, we simply take the running count and divide by the number of decks left to be dealt. This number is called the true count. And here's the surprisingly simple formula that relates the true count to the expectation at the given point of the game. And this formula contains some really good news. A true count of 2 or greater means that our expectation is positive, right? 2 minus 1 is positive. A true count of plus 10, which can easily happen just before the shuffle, means the expectation is 4.5%, which is pretty amazing. So what does the card counter do? Well, ideally she bets little or nothing when the true count is negative, makes small bets if the true count is slightly positive, and then larger bets when the true count is higher. The bad news is that betting in such a manner involves a lot of boring waiting around, followed by frantic and really suspicious betting, perhaps hundreds of dollars on a few brief hands. How well does it work? Well, these days a typical betting scheme going up to, say, a maximum bet of $200 might result in an average of about $15 an hour. Wow, not what I would call a great hourly pay. And it gets worse. The result in any given hour can differ massively. you can expect a standard deviation, a typical plus or minus, to be about $500. Of course, the way card counters bet makes them very easy to spot, and Marty has had his run-ins with casinos. So unless you're part of a well-drilled team of counters and players, or you're really good at disguises, there's a fair chance you'll get to meet some burly casino employees within a few short hours. Well, we did say Blackjack weighs a way to win a small fortune. Good luck, happy gambling, and that's all for today. Except we've all heard that back in the 70s there were lots of people making millions of dollars playing blackjack in the casinos. So what has changed? Why can't we make millions of dollars these days?
Well, the casinos have gotten a lot more careful and a lot smarter. They use more decks, which means the running count matters less. The true count's slower to get going. They use automatic shuffling machines. They're really on the lookout for suspicious betting. So unless you're incredibly good at disguising yourself, incredibly good at team playing, it's pretty much dead.
Oh, it's dead. Okay,
Yeah.
no, sad.
Yeah.
But what about other games? There's online gambling now. So are there ways to make money with gambling these days?
Absolutely. Yeah, the casino's always looking to sucker more people into betting and suckering old people into betting more. So there's always promotions, there's new games, new rules. Some are knowingly have expectation, which is positive, and they just watch out. Others, the casino makes mistakes, or online betting sites make mistakes. So you do a little expectation calculation, and often, not always, but often, you can find a little edge. And enough of these little edges, and you can make a nice little profit on the side. And definitely there's some people who just computerize everything, calculate to the nth degree, and there's some secret people, I'm sure, who are doing very, very well.
All right. Well, that's a perfect lead-in to our next video at some point. But anyway, thanks, Marty, for coming today.
Thank you.
And we'll have you again, sure.
Cool.
Cool.